I wanted to give you a little help with this linear programming homework. I've chosen 3 problems that we're going to do in this video. And this is page 138. And as you can see, this is number 5. So let's just work through this one. I've got the system of constraints given here. And we'll try to color code them so you can maybe keep up with the different lines and how the shading goes. So let's start with this red inequality. It needs to be solved for y. And when we solve for y, we get y is greater than or equal to negative x plus 8. So obviously we're going to do a y-intercept of 8 with a slope of negative 1. And we'll go ahead and draw this line. There's the boundary line. And the shading for this, the greater than side for this line is above. So I'm just going to show arrows going in that direction for the above side. Okay, and now let's take a look at this inequality y is greater than or equal to 5. Well, first of all, let's do the line y equals 5, which is right here. Just crossing 5 on the y-axis. And the greater than side for this blue line is the upper side. So we can see so far that our red and our blue shadings will converge in this area up here, greater than for both. And then finally, let's do in green this last inequality that is x is greater than or equal to 0. Well, here is where x is 0, just on top of the y-axis. And the greater than side for that will be to the right. And so what we end up with is our shading would be all of this area where blue, red, and green all converge. Okay, so this is an unbounded region, just continuing to go on, but we're obviously only going to shade up to a certain point. So this is a little different than what we had before. Our other problems had triangular shapes or squares, rectangles, but this one actually doesn't have an end, a boundary going on and on in this upper quadrant 1 direction. So we still need to identify vertices. So our vertices are located here. We have a vertex there where 2 lines cross on the feasible region. Remember, this is called the feasible region here. And so that's the point 0, 8. And then we got another vertex where the red and the blue cross on the feasible region. And that's the point 3, 1, 2, 3, 4, 5. The point 3, 5. Okay, so in this case we only have 2 vertices. And our job is to minimize the given function. So let's test each one of the vertices, starting with 0, 8. I'll do 3 times 0 plus 2 times 8, and that gives me 16. And then for the other vertex, I've got 3 times 3 plus 2 times 5, and that's 9 plus 10, which is 19. So obviously the ordered pair or vertex that minimizes the given function is the point 0, 8. So I've identified that as our minimum, and the minimum value is 16. All right, so that should be your solution to number 5. Okay, what about number 11? Or I'm sorry, number 16. I was looking over here. This is number 16 on page 139, and I want you to pay close attention to how this one is going to be a little different when the graph is done. That's going to be a little extra required of us. So we'll start with getting the red inequality set up for graphing. So we're going to subtract x from both sides. So that gets us a y-intercept of 11. Well, this is 10, and I'm just going to make another mark to represent 11. So you won't have to change your units. And then we'll count a slope of -1, which is down 1, right 1, down 1, right 1. And let's draw this red boundary line. Make sure I got all my points lined up properly. I think they're right. Okay. And then when we do the shading, the less than side is below the line. So I'm going to just show that we will be shading in this direction when we do our shading. Okay, for the blue, let's solve it for y. And we're going to multiply by 1/2 on both sides. Y is greater than or equal to 1/2 x. So that's a y-intercept of 0 and a slope of 1/2, up 1, right 2, up 1, right 2 again. And so here's the boundary line. And the shading for this inequality, the greater than side is above the line, so that means this side. So you can kind of get an early picture that red and blue are converging in this area. Okay, now we've got these other two constraints that I've got colored in green. If we're going to do x equals 0, the boundary line x equals 0 looks like this. And if we shade that, the greater than side is this way. All right. And y equals 0 is this horizontal line. It's just right on top of the x-axis. And the greater than side for that is this way. Okay. So we're interested in where all four shadings converge. Where do they all four gather up? What area do they all four share? And that's going to be this area right here, this triangle above the blue until you get to the red, and then it's bounded on the left side by the green. So this is our feasible region. Okay, so let's see what the vertices are. Right up here at the top, this was the point 0, 11. That's a vertex where two lines meet. Down here, we have the origin as a vertex, 0, 0. And then this is the interesting one, because just by looking at the graph, I really can't tell. And I can't guess. We had something like this come up the other day, and it looked like it was a half, and it turns out that it was. But we can't just look at this and guess and say, that looks like a fourth, or that looks like a third. We have to know exactly where those two lines cross, the red and the blue. Well, at this point, I'm not worried about inequalities because that just tells me where to shade. What I'm interested in is the equation for the red line and the equation for the blue line. All right, so the equation for the red line, if you just replace that inequality with an equal sign, the red line equation is y equals negative x plus 11. And the equation for the blue line is here as y equals 1/2 x. Well, the graphing method here does not give me a definitive answer as to where this vertex really is. So I'm going to have to rely on one of my other methods for solving systems, and that means either substitution or elimination. And since both of these are already solved for y, to me it makes sense to use substitution. I can substitute 1/2 x in blue into this red y. That's really what substitution says. Solve for one variable in one equation and replace that variable in the other. All right, so let's see if we can find out what x is. So substituting y, I get 1/2 x equals negative x plus 11. Okay, and I'm going to eventually need to add 1 to both sides, but it'd be nice if this were a fraction the same as this with a denominator of 2. So I'm just going to rewrite this as negative 2 over 2x plus 11. It still equals negative 1, but now it's got the same denominator. That's what I will be adding to in just a moment. Okay, let's just come up here. Adding 2 over 2 to both sides gives me 3 over 2x equals 11. And now to solve for x, I'm going to, maybe I'll change color if this will show up a little bit better. Remember the inverse property of multiplication, I need to multiply by the inverse 2/3 on both sides. And that gets me my solution for x, which is 22/3, or as a mixed number, it's 7 1/3. Well, let's see if that's reasonable according to our graph. According to our graph, our x goes about right here. So let's see, 1, 2, 3, 4, 5, 6, 7, and it's just a little beyond 7. And yeah, I think that's very reasonable to say that that's 7 1/3. Okay, so my x-coordinate of this vertex, I'm just going to leave it as a improper fraction. It's 22/3. Well, what about the y? Well, if we know what x is, then it's easy enough to solve for y just by replacing either one of these x's with 22/3. All right, so let's just say, for example, the blue, y equals 1/2 times 22/3. Okay, we can do a little canceling here because 2 goes into both of these numbers, and we end up with 11/3, or in mixed number form, that's 3 2/3. Well, let's see if that's reasonable. Here's our x at 7 1/3. Now, how far does it take us to get to that point? Going straight up, 1, 2, 3, and yeah, I would say it's almost up to 4, just a little bit short of 4. So looks very reasonable that would be 3 2/3. So I'm going to express the y coordinate of this vertex as 11/3. Okay, I think you can take it from here. You're going to test all 3 of these vertices in this profit function, just like we did previously. The x in for x, y in for y, and you're asked to find the maximum. I'll just go ahead and tell you that the maximum should be this point, but you need to be able to tell me what the actual maximum number is. So once you've tested them all, you should understand how to use these vertices to determine which one is the maximum vertex, or which one gives us the highest value for P. Okay, so hopefully that helps you with that, and let's try number 18, and this will be our last one on this video. So we got several constraints to graph. Let's just jump right in. Taking this red one, solving it for y, we get y is greater than or equal to negative 5x plus 10. And so once again, we said 10 is up here right at the top of our arrow y-axis. And let's do a -5 slope. So 1, 2, 3, 4, 5, and right 1. 1, 2, 3, 4, 5, right 1. All right, and line those up. And that's the boundary line. And when we do our shading in just a little bit, the greater than side is this side. Okay, now let's do the blue. We need to subtract x from both sides. Y is greater than or equal to -x plus 6. So let's go to 6 on the y. -1 slope. And sketch it. Okay, and we'll go ahead and just point in the direction of the shading. Greater than for the blue is also going this way, this side. So it looks like we have red and blue coming together in this region so far. Okay, now I've got this weird looking color. Not sure what it is, but it's different. So let's solve for y. So we got 4y is greater than or equal to -x plus 12. So y is greater than or equal to -1/4 x plus 3. Okay, so 3 on the y-axis, -1/4 slope, down 1, right 4, up 1, left 4. Here's that boundary line. And it's also greater than, so when we do the shading, it's going to go in that same area as the red and the blue. So far, we've got this region that will be shaded. And then we've got these other two that we've already looked at before. X equals 0. I'll change my colors. Here's x equals 0. And we'll be shading to the right. It's just going to reinforce where we're already shading. And here is y equals 0. And we're shading above. So again, when we put all these shadings together, all of them combine into this region. We can't go below the blue. We can't go below that reddish maroon. And this is another one of those unbounded feasible regions. It goes on forever and ever in this direction. But really all we're interested in is taking the vertices and seeing which one will give us a minimum value for the function. This is a C function, probably stands for cost. We're usually wanting to minimize cost and maximize revenue. So I'm going to get the vertices off of this, and then I'm going to let you take it from there. I think most people understand how to get the values of C, and you're looking for the lowest value of C. Okay, so we got a vertex up here at 0, 10. There. We've got a vertex here at 1, 1, 2, 3, 4, 5. All right, and still on the feasible region, we've got a vertex here at 1, 2, 3, 4, 1, 2. And then way over here, I'm not sure based on the graph paper. If I just had some bigger graph paper, it would be nice, but I can't tell for sure where that's going to cross. I mean, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Not really sure. Well, here's how I can know for sure. Okay. Again, look at the equation for the two lines that are going to cross each other. Well, this one's easy. This line here is the line y equals 0. The other line that's going to run into it is this line that says -1/4 x plus 3. Okay, so how do we solve a system? That's really what we want to know. Let's find x and y. Well, we know what y is of this point of intersection. That's got to be 0. But what's the x? Well, let's do substitution and find out. Y is 0, so that means I can replace the y in the bottom equation with 0. Okay, subtract 3 from both sides. Multiply by the inverse of -1/4 on both sides, which is -4. And lo and behold, we know exactly where what the x coordinate is of that point. It's 12. So my other vertex, make a little bit more room. That final vertex there, the bottom right-hand side, is 12, 0. Okay, right in there. So 1, 2, 3, 4 vertices, and I want to see if you can test each one, 0, 10, 1, 5, 4, 2, 12, 0, which one would give you the minimum for C if you plug those numbers into this given cost function. Okay, and we'll see on next time if you got that correct answer, but at least hopefully you understand how to come up with the graph of the constraints and then how to find the vertices. So hope this helps, but if you need more help or if you have any questions, just let me know.